This week's meteorology lesson is going to be on global winds. You can see from this little scientifically accurate representation of the globe here from satellite data, you can see how basically overall the wind on the Earth, the atmosphere kind of swirls in some general patterns that we can see here. So we're going to talk about that this week. As usual, remember that red slides mean you have to take notes. You should have your Inner Planets handout to go along with this, and don't forget to look for the owl. At the end, make sure you tell me where the owl is and summarize what you've learned in a few sentences. So the first thing that we need to understand is that overall air flows from the poles to the equator, from the poles up here down towards the equator down here, and from the pole down here up towards the equator up here. So from the top and bottom of the Earth towards the middle of the Earth. But why is this? All right, what you've learned so far, you should be able to answer this question. Think about this picture. Why do you think that that happens? Well, we have, this would represent the poles, right? Cold air sinking, and that has to do with higher pressure, and near the equator we have warm air rising, and that has to do with lower pressure, and you know that this is due to differences in air pressure. The air is going to move, generally speaking, from high pressure to low pressure. Now it gets quite a bit more complicated than this, as you're going to see, but overall that's kind of the basic idea of how air wants to move on Earth. It wants to move from the high pressure polar regions, cold, high pressure sinking air, towards the warm, low pressure rising air area of the equator. Again, this is an example of that idea of the sun heating the Earth up unevenly and causing weather patterns to happen. So we've seen this before. So remember, high pressure to low pressure, air moves from high pressure to low pressure, kind of like this. High pressure to low pressure, high pressure to low pressure, high pressure to low pressure, and so on. So we can kind of see this idea happening here on a small scale, but it also happens on a very large scale on the entire Earth. So speaking of the entire Earth, here we have the entire Earth. So basically what we have is the idea of high pressure at the poles, high pressure up here, H for high pressure here at the poles, North and South Pole, because of that's where it's cold. And we're going to have low pressure here, low pressure here, low pressure here, low pressure all the way across the equator right here. Okay, and so air, generally speaking, is going to want to move from high pressure towards the low pressure. Then what happens to warm, low pressure air? It rises, right? So it's going to rise at the equator and basically come back towards the high pressure area of the poles. And what happens to cold air? It sinks. So you have this giant convection current going on here. And notice for us here down on the Earth, the air is generally moving from the poles towards the equator and then rising at the equator, moving back towards the poles and sinking again. Same thing with down here. You're going to have from high pressure to low pressure. Near the Earth, it's going to move like this, from high pressure towards low pressure, then it's going to rise at the equator and come back towards the poles and sink again. Okay? And if we're looking at it from here, you would see it moving sort of down from high pressure towards low pressure, and again it would get here, rise up, and come back to the poles and sink. Now, I want to point something out here though. I want you to notice as I move this line, the wind is moving. Notice what the Earth is doing underneath it. The Earth is actually moving underneath the air, and so this is an interesting thing. So the air kind of hits the top of the United States right there, but by the time it gets to the bottom of the United States, it's kind of off to the west a little bit more. So this is kind of an interesting idea. This is what's called the Coriolis effect, and this is what we're going to see here is the idea of it looks like the air is curving because of the rotation of the Earth. So take a look at this clip.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Okay, so hopefully that makes sense. You see the idea here. This is kind of a complicated idea. We'll go over this much more in class, so don't worry if you don't fully understand it now. But basically, what the main things that you need to know is that the Coriolis effect causes the air to appear to curve. It's not that it's actually curving, it's more that we're moving underneath the air. But from our perspective, it looks like the air is curving. And the way that it curves is to the right in the northern hemisphere, and it curves to the left in the southern hemisphere. Now, first of all, if you're looking at this, you might be saying, but Mr. Goodstein, it looks like the air in the northern hemisphere is curving that way, which for me is my left. Well, in order to kind of figure that out, I'm just going to flip this over real quick. There we go. And I'm going to put the arrows back in the right place. So it's curving to the right in the northern hemisphere, right? This is still the northern hemisphere. And this is still the southern hemisphere up here. I just flipped the Earth over, or I flipped you over. You could think of it that way. And now what you see is that, yes, it does in fact curve to the right in the northern hemisphere, okay? You have to think of it from the perspective of the air, like you're in a car driving in the direction that the air is going. This would be a right turn. And this is still, if you're in a car going this way, this is a left turn for that car. Okay? So you got to kind of just picture it from the perspective of being the air, or like think of it like you're a car going in the direction that the air is going. So, Coriolis effect is the apparent curvature of the air due to Earth's rotation. Nice. And in the northern hemisphere, you need to know it curves to the right. Southern hemisphere, it curves to the left. Very similarly to when we talked about the idea of seasons and all that kind of stuff, I think it's probably your best bet as far as memorizing this to just remember what happens in the northern hemisphere. Northern hemisphere is a right turn. Just like with seasons, everything's opposite in the southern hemisphere when we're talking about this. All right, take a look at this map, and I want you to see if you see any sort of patterns to this. Take a look at it, look for some patterns maybe. Take a look at these high pressure areas here, here, and here, right? And high pressures here, and high pressures kind of in this area here, right? Down here we have low pressure. Over here we have some low pressure, right? So what we can see here from this image is that we see basically bands or bars or rows of high and low pressure here that seem to kind of line up in straight lines. Now, where's the equator? You should know this. You should be able to look at this map and know exactly where it is, right? It's at the 0 line right there. Okay, so there's the equator. Remember what we said about how air moves. What kind of pressure would we expect to see there? Well, that's warm, rising, low pressure air at the equator, right? So temperature and pressure at the equator is high temperature and low pressure, rising air. Okay, so if we look at this and kind of compare that map that we were just looking at, this is the same map over here, it's just kind of squished now, and look at it from sort of a side view of the actual Earth, right? So here's the equator right here, there's the equator, and what we have, if we're looking at the side of the Earth, is rising air right here, right? But what do we have here? Well, we have high pressure areas, right? So the air is going to move to that area down here. And when it gets to that area, it's going to start sinking, and we're going to have these little mini convection cells within that big convection cell of the air moving from the poles to the equator. And right here we can see in this area there's another band of high pressure, so that's going to kind of rise up here at the equator and sink at the high pressure areas, right? And here it's going to be sinking at that high pressure as well. And up here we can see that there's more low pressure, so it's going to be rising there. Always, the air is always rising at low pressure areas and sinking at high pressure areas. And at the on the surface of the Earth, it's going to be moving away from high pressure areas and towards low pressure areas. Away from high pressure, rising at the low pressure, moving back over here, sinking at the high pressure, then moving away from it towards the low pressure, and you get a nice circular convection cell going on there. Now, when you look at this, you got to kind of be able to think of it from this perspective here, looking at it from kind of out in space, and you also need to be able to think of it from this perspective here, like if you were standing on the Earth. Okay, so think of it kind of like this, like a big wave, and we're kind of inside this wave, right? So high pressure sinking air moves towards low pressure, rises, low pressure, warm air rises, cold air sinks, convection. Okay, so primary high pressure and low pressure areas, we get an equatorial low pressure trough. That's what they call that because it's low pressure there. All right, think of a trough like what pigs and horses eat out of, right? Kind of looks like a big long low area. Okay, so we get low pressure at the equator, and then we have high pressure cells at the poles, and in between those guys we have subtropical high and subpolar low pressure cells. Now, I want you to think about what we've learned so far. Number one, that air wants to move from high pressure to low pressure. So it's basically going to want to move from these high pressure. So for example, right here, it's going to want to move from the high pressure area towards the low pressure of the equator. But also remember that the air is going to kind of turn to the right in the northern hemisphere. So again, this is kind of a right turn here. So in general, we're going to get some air moving kind of in this direction from sort of northeast to southwest, like that. So sort of in that direction, right? Now here we have high pressure moving towards low pressure, but again, it's going to take a right turn. So it's going to kind of move in that direction there. Right here, we have, now we're in the southern hemisphere, so high pressure to low pressure, and that's going to take a left turn. Kind of go this way. High pressure to low pressure, and turn left, because you're in the southern hemisphere. High pressure to low pressure, turn left due to the Coriolis effect in the southern hemisphere. Okay? Here, again, high pressure to low pressure, but a left turn. And again, if you're getting confused why I'm going sort of, it seems like I'm going in a different direction here, remember, this is a left turn if you are in a car driving this way. You're turning left there. Left turn. High pressure to low pressure, and left turn in the southern hemisphere due to the Coriolis effect. So we get winds kind of moving in this direction here, and in this direction near the equator, right? And kind of this direction here. Okay, I want you to take a look at this next clip and take a look at this. You can actually see this happening in this actual video here of the Earth seen from space. You can see the clouds moving around in this way. So once again, this is going to be the general movement of air on the Earth. We get these basically these bands of movement that primarily are driven by the fact that air wants to move from high pressure to low pressure, and then also the fact that the Earth is curving makes it turn to the right in the northern hemisphere and to the left in the southern hemisphere. These are the kind of the two basic ideas of why the air overall in large waves on kind of a large scale on the Earth, why the air moves the way it does, why the atmosphere circulates the way it does. It's well, I guess we can go back one more step and say it starts with the uneven heating of the Earth by the sun. That's the first thing. That causes differences in air pressure. Air wants to move from high pressure to low pressure. And lastly, it's complicated a little bit by the fact that the Earth is spinning, and that creates the Coriolis effect, which makes it seem like the air is actually curving to the right in the northern hemisphere and curving to the left in the southern hemisphere. All right, so you ready? You got your pencil sharpened? We need to draw a bunch of stuff here. We're going to draw this out, okay? So start off. Hot air rises, and draw those two little convection cells here. Please be very particular about the way that the arrows are going, where you place the arrows, where you place the little circles, and where you place these words like hot air rises. Make it look exactly like what I have on the screen here. All right, so cold air sinks at these high pressure areas. Notice the arrows and which way they're going, right? The arrows are going this way, and it's going to sink down here. And these arrows are going this way, and it's going to sink down here. Why are the arrows going that way? Because you have low pressure. You have the low pressure over here, which forces the air to go in that direction. From high pressure to low pressure, this is a high pressure area here. And this is a low pressure area here, so air wants to move this way, and then it circles back around that way, sinks at the high pressure, and rises at the low pressure. All right, so let's finish this up here. I'm going to kind of go through these fairly quickly now so that you can kind of basically look through this, and then you can pause it and fill everything in. Okay, there's our low and high pressure areas. There's our convection cells, cold air sinking, hot air rising. All right, so now, talked about this, right? Which way is the air going to go? Well, let's start off, how about we start off right here, okay? That's a high pressure area, so it's going to want to go away from high pressure towards low pressure, there and there, right? Away from high pressure towards this low here. Ooh, sorry, that wasn't very well drawn. And this low here, okay? But what's it also going to do? It's going to curve to the right because we're in the northern hemisphere. So it's going to curve to the right, and it's going to curve to the right, curve to the right. Okay, so that's a starter. Okay, that's basically the idea here. Now, I'm going to show you the slides here that show you how this works, but right now, if you want a little challenge here, pause the video right now and see if you can, don't draw it yet, but see if you can figure out how these arrows will look in all of these different bands here. Okay, it's a little challenge for you that'll help you to remember this and help to see if you get this idea. All right, so if you paused it, welcome back. Hopefully you tried that out for yourself, but here's the answer for you. Okay, so make sure you draw these arrows in how I have them on the screen. Now, we have some names for these. Okay, so these are going to be called the trade winds. Then we have these ones here. Okay, again, from high to low pressure and curving to the right in the northern hemisphere, curving to the left in the southern hemisphere. These are called the westerlies. And then one more, we have the polar easterlies. Okay. All right, one more thing about this. I think this is a really interesting connection here to something that we did in astronomy. Hopefully you know what this is a picture of right here. And maybe you even know what that is right there. How many of you said Jupiter? And that's the great red spot, right? Okay, so take a look at this here. Doesn't this look like what we've just been talking about? The thing about it is on Jupiter, you can actually see the gases. On Earth, you just can't see them because they're not visible. But this is really what, if we could see air, this is what the atmosphere of the air would look like. It would be moving around in the same way Jupiter does. And by the way, it's for the same exact reason. If we look at this, I think something really interesting about this picture over here is this is, if you can read this, I know it's kind of blurry and small, but this is from NASA's Infrared Telescope Facility. Infrared, that means it's showing heat, and it says the bright spots are due to heat radiation escaping from Jupiter's interior regions. Now, what that means is, in sort of plain English, is that these areas here are hotter than the dark areas that you see, okay? And notice that you can actually see that the gases have actually sunken down in these darker, colder areas, right? Cold, high pressure, sinking air. You can actually see that here. And we would expect that air would be rising in these areas and sinking in these areas, right? And we would expect air to be moving from high pressure towards low pressure. And we would also expect some sort of curvature to happen where this air would also be kind of curving from left to right or from right to left, depending on which way Jupiter is spinning. I'm not really worried about you figuring all that stuff out, but you can kind of see it from these bands here. So, same exact thing happens on Jupiter. Same exact thing happens on any planet that has an atmosphere that's made of gases, and it all happens for exactly the same reason. Uneven heating by the sun causes differences in air pressure. The air moves from high pressure to low pressure, and then because it's spinning, you have the curvature of that air, or at least the apparent curvature of that air, due to the Coriolis effect. So that brings all that together. Make sure you know that part. And there you have it. Global winds. So overall, the starting point is that global winds move from the poles to the equator. This is caused by differences in air pressure due to the equator being heated more than the poles. That creates high pressure near the poles and low pressure near the equator. So you get low pressure, warm, rising air at the equator and high pressure, cold, sinking air at the poles. This is complicated a little bit by the spinning of the Earth. This is called the Coriolis effect, and this is the apparent curvature of the air due to the Earth's rotation. Remember, in the northern hemisphere, it curves to the right, and if you're just going to remember one thing, that's the thing to remember. But the southern hemisphere is opposite. It curves to the left. We talked about global wind patterns. Make sure that you understand why the air moves the way it does, and make sure you understand where the different wind patterns are in the different directions. We talked about the trade winds, the westerlies, and the polar easterlies. We'll talk more about this in class this week, and I will see you then.